Okay, gang, the next type of function we're going to be looking at is something called the rational function. This is where I have a polynomial divided by a polynomial. Of course, we understand that q of x cannot be 0. Other than that, it's the form p of x divided by q of x. Okay? Rational function. We want to look at the domain and range of rational functions, but right now we're just going to look at the domain. Okay? Basically, we want to look to make sure that the bottom is not 0. Okay? And we also, this is only true if the rational function is in simplest form, then the locations of where the denominator is 0 are also the locations of the vertical asymptote. So the domain of r of x, in this case, looks like x can't be -5, right? I take the denominator, I set it equal to 0. That gives me x equals -5. That means if I put -5 in here, I get 0 on the bottom. So the domain is all reals. We can write it different ways. We can write all x's such that x is not equal to -5. Okay, that's set builder notation. Or we can write -infinity to -5, parenthesis, meaning not including -5, in union with -5 to infinity. Okay, in this case, where is x squared minus 4 equal to 0? That's when x squared equals 4. So I get plus or minus 2. Most of the time then we write it in set builder notation. We say the domain is all x's as long as x is not equal to -2 and x is not equal to 2. That's a little nicer to do. When there's two excluded values, it's hard to write it in interval notation. It just starts looking long. You can do it, of course, if you want. I would, of course, accept it. -infinity to -2 in union with -2 to 2 in union with 2 to infinity is how I'd have to write that. And like I said, when it gets extra long, sometimes people just say, you know what? I'm going to write it in set builder notation. It's a little easier. Okay, the domain of this one, ooh, 1 is x squared plus 1 going to equal 0. That would be when x squared is -1. We're talking about real numbers here for, the domain. I can put anything I want. In this one, the denominator is never going to be 0 because x squared is never going to be -1 in the real number system. Okay, in this case, guys, okay, so in this case, if I want to say what are the vertical asymptotes, this vertical asymptote will be x equals 5. The vertical asymptote is x equals 5. Okay, the domain, this is saying if the rational function is in simplest form, then the domain, what the excluded values of the domain are also the locations of the vertical asymptote. There'll be two vertical asymptotes here. X equals -2, okay, a vertical line straight down at -2. We usually dot it, right, for an asymptote. And the other vertical asymptote will be x equals 2. Here, there are no vertical asymptotes. It's all reals. This one's a little different. Okay, the domain is all reals except 1. Okay, so I might, oops, how am I doing that? I might say -infinity to 1 in union with 1 to infinity. However, x equals 1 is not a vertical asymptote because I can simplify this, right? What's x squared minus 1, guys? Difference of two squares, right? So I can make this x plus 1 divided by x minus 1 all over x minus 1. And then I notice the x minus 1's cancel. the answer to this question, or the simplified version of this, is just x plus 1. Well, then it seems like the domain would be all reals, doesn't it? It's not all reals. This is my function. I can't put 1 into it. After I simplify it, I can. I get that. But I can't right now. So the domain still remains that x cannot equal 1. However, x equals 1 is not a vertical asymptote. Not a vertical asymptote, because it says if the rational function is in simplest form, then these are also the locations of vertical asymptotes. What happens, guys, is x equals 1 ends up just being a hole in the graph, okay? Not a vertical asymptote. Let's remember what basically the graph of a rational function looks like. Here's sort of the parent graph. Y equals 1 over x. Okay, so I can't have 0. That's my vertical asymptote, right? I could put 1 in. 1 divided by 1 is 1. I could put 2 in. 1 divided by 2 is a half. I could put 4 in. 1 divided by 4 is 1/4. You can see what's happening. It gets closer and closer to 0, but it's never going to hit it. On the other end, if I put -1 in, 1 divided by -1 is -1. If I put -2 in, 1 divided by -2 is -1/2. Okay, now if I put numbers close to 0 in, like 1/10, 1 divided by 1/10 is 1 times 10, or 10. If I put 1/100th, I'm at 100. Okay, same thing happens in the negative, when I put -1/2 in, etc. Okay? Everybody all right? So this is our parent graph. We actually have a horizontal asymptote at y equals 0. Okay? Vertical asymptote is x equals 0. That's this vertical line. Horizontal asymptote is y equals 0. It's a horizontal line. Okay? Now, interestingly enough, if I just square the x, look what happens. This part that was down here, it just flips up. I still have a vertical asymptote of x equals 0. I still have a horizontal asymptote of y equals 0. But it looks a little different because x is squared, so it's never going to be negative. Those are just some parent graphs that you should have in your head. Okay, here we go with this notation with infinity again. As x approaches negative infinity, or as x approaches infinity, if the values approach some fixed number, then that's what we call our horizontal asymptote. Okay? As x approaches infinity, we kind of see what y is getting close to. And then we start putting negative huge numbers in, and we see what y is getting close to. Just like back here. What happens is when I let x be huge, like 1,000,000, y is getting really close to 0, isn't it? 1/1,000,000th? It's pretty tiny. Okay, the bigger x got, the closer y got to 0, but never hit it. Also, the smaller x got, 1 over -1,000,000, the closer I got to 0. So that's what that means. As x is getting closer to negative infinity or positive infinity, what is y getting close to? Okay, so try that with these 3 functions. Put 100 in, put 1,000 in, and see what you get close to. Put 100 in, put 1,000 in, and see what you get close to. Okay? Okay, so I put 100 in for x. I got 0.02, 6 over 303. Then I put 1,000 in for x. 6 over 3,003 was 0.002. Then I put 1,000,000 in for x, and I got 0.00000. Can you see that the y, as the bigger x gets, the closer this gets to 0? I'm getting very, very tiny. right? So the horizontal asymptote here is y equals 0. Here I put 100 in for x, 600 over 303, I got 1.98. I put 1,000 in for x, I got 1.998. I put 1,000,000 in for x, I got 1.999999. Aren't I getting closer and closer to 2? The horizontal asymptote here is y equals 2. Now in this case, I put 100 in, I got almost 20. I put 1,000 in, I got almost 2,000. This is just getting bigger and bigger, so there is no horizontal asymptote. Okay, so what you'll notice is a little pattern. If the degree of the numerator is smaller than the degree of the denominator, in other words, this degree up here is 0 because there is no x term, divided by a first degree. So when the numerator of the numerator's degree is smaller than the denominator's degree, the horizontal asymptote will always be y equals 0. When you have the same degree on top and bottom, this is a first degree and a first degree, then you simply divide those coefficients. 6 divided by 3 is 2. This other 3 is irrelevant. That could be a 5. It doesn't matter. This is still y equals 2. That could be a 25. It doesn't matter. The horizontal asymptote is y equals 2. 6 divided by 3. You divide the leading coefficients. If the numerator's degree is bigger than the denominator's degree, then there is no horizontal asymptote. I have that here for you. If the degree of the numerator is less than the degree of the denominator, y equals 0 is your horizontal asymptote. If the degrees are the same, y equals the quotient of the leading coefficients. All right, so it was 6 divided by 3, or y equals 2. If the degree of the numerator is bigger than the degree of the denominator, no horizontal asymptote. Okay? There's actually an oblique or a slant asymptote if the degree of the numerator is exactly 1 more than the degree of the denominator. Exactly 1 more than the degree of the denominator. Okay, so we still say there's no horizontal asymptote. That's true. But there is a slant one if, like, you have a third degree over a second degree, like exactly 1 more, a fifth degree over a fourth degree. Then there still will be no horizontal asymptote, but there will be a slant asymptote, an asymptote that's like a line. We'll get to that then. All right, so let's look at this one. Right away, we want to know what the domain is. So I'm going to set 2x plus 7 equal to 0. 2x equals -7. It looks like it's all x, except x can't be -3.5, right? Sorry, I didn't finish. -7 divided by 2. So at -3.5, I'm going to drop a vertical asymptote. Oh yeah, because this is simplified, right? I want to make sure it's simplified. Vertical asymptote at x equals -3.5. Horizontal asymptote, well, the degrees are the same. So I'm going to divide the leading coefficient. There's a horizontal asymptote at y equals 1.5. Yes, you have to write y equals. Okay. Oblique asymptote, no, there is none because they were the same. All right. And I'm just going to plot 2 points on the opposite sides of my vertical asymptote. When I put 0 in, I got 0. When I put -5 in, I got 5. And I'm going to let my asymptotes guide me.